Hello everyone. Today I present our work on how to combine LiDAR with imagery data to improve on the quality of geospatial deliverables. My name is Zoltan Koppanyi and I'm with PixElement. We are developing a cloud and desktop-based photogrammetric processing software. The work I'm presenting today is available in our software solution. First, let's start with why would we want to combine LiDAR and photos? Let's compare the two sensors. Both sensors have their advantages and disadvantages. LiDAR is an active sensor, meaning that it is more reliable in changing lighting or weather conditions. It's also more reliable when it comes to object textures, and it is able to penetrate through vegetation and so allowing us to map areas under canopies. However, it does not capture color, only intensity information. On the contrary, in photogrammetry, we use cameras, which are passive sensors, so lighting and weather conditions have influence on our final product. But cameras can capture color information. Cameras are also cheaper than LiDAR sensors and lighter as well, so that means cheaper hardware. The other main difference between the two sensors are that the LiDAR uses direct georeferencing to transform the sensor observations into the mapping coordinate system. On the contrary, photogrammetry uses indirect georeferencing, which is considered a more consistent and often more accurate georeferencing approach. We can also compare the two sensors based on the typical deliverables. LiDAR drone systems typically provide only point cloud that might not be even colorized. In contrast, photogrammetry serves us with various products including color point cloud, texture 3D mesh, and orthomosaic. We can take advantage of both worlds by combining LiDAR and photogrammetry, and that's what today's presentation is about. Now let's look at how we do this. First, we need to realize that image metadata, the mapping coordinate system, which is the coordinate system of the ground controls, and the LiDAR's coordinate system can be different. In fact, that's what we always see when we look at these data. Therefore, we need to figure out the way to align these different data into one common coordinate system. So when we look at how others combine these two data sources, common approach is that they just filling up missing areas of the LiDAR point cloud from photogrammetry. So this assumes proper alignment of the systems. In contrast, we take the images and the LiDAR LAS file exported from the vendor processing software, and then we provide an interface for our users to find matching points on the photos and in the LiDAR cloud. And based on these matching points, we can compute an initial transformation between the LiDAR and the photo system, and then use these match points during the bundle adjustment. So the first thing that a user needs to do is to find matching points in the point cloud and on the photos. So we provide a user interface that makes it easy to pick matching points. Here we can see this interface on the slide. On the left, a point is picked from the top of a trunk, and the same point can be selected on the photos. The main disadvantage of this approach is to find good points that can be easily identified on the photos and in the cloud. It is a difficult task to find these points because points that are easily identifiable on the photos might not be visible in the cloud and vice versa. For example, in photogrammetry, we use special targets or existing points on the ground that can be found easily on the photos. But with LiDAR, we need to use targets, which has different retroreflectivity than the surroundings, so these targets pop out from the intensity cloud. So how should we pick points then? So we can find texture transitions in the scene that also have different intensity properties, like the example in the slide. These are good features for our matching approach. Another example of good points is locations where the structure changes. Such an example is the corner of building roofs. These are easily identifiable in the cloud as well as on the photos. After we match the photo and LiDAR points, the photo 3D coordinates can be computed based on the initial photo network structure from motion. Then we compute the transformation between the LiDAR points and the photo points and bring these points in a common system using the estimated transformation. Our experience is that X, Y, Z translations as a transformation or alignment model is appropriate in most cases because commercial drone LiDAR systems can already provide a relatively good orientation for the point cloud. Next, the photo network is adjusted where the match points are also fixed during the bundle adjustment process. Then this will fit the camera extrinsics to the picked points, so the photogrammetric network will also locally fit to the point cloud, not just globally. First, if we don't have GCPs, one might want the final product's reference to the LiDAR or to the photo network. In an ideal case, when the photo and LiDAR mapping systems are the same, this will only mean that which sensor's positioning system we trust more. The LiDAR coordinate system might be desirable if we trust in the LiDAR georeferencing. However, if the camera drone uses RTK, we might want to fit the LiDAR model or a LiDAR cloud to the photos. In reality, we see that the LiDAR and photo data that we receive can be delivered in different height systems. Our method can easily account for this without taking any additional step. However, choosing the proper system to reference to becomes more important in this case. I didn't talk about the case when the project has ground controls or GCPs. If we have GCPs, then first we georeference the photo model to the GCPs by solving the bundle adjustment without any LiDAR input. Then we compute the matched points coordinates in the georeference photo network. Afterwards, the initial transformation is computed based on the match points, and then these points are transformed into a common coordinate system. And finally, another round of bundle adjustment is performed with the GCPs and the transform match points. Therefore, the final deliverables will be in the GCP's coordinate system. Now let's see some examples how the presented approach can help us to deliver better geospatial products. First, in many cases, LiDAR clouds come without color. The presented approach allows to colorize point cloud. LiDAR systems often comes with camera, so a processing software can colorize the point cloud using the images from this camera. However, the colorization is often incorrect due to inappropriate bore side calibration or due to drift effect of the LiDAR systems. We can see some examples of this on the slide. Our method can be considered as a form of indirect georeferencing, so we can mitigate or eliminate bore side or drift issues and provide a more consistent colorization. In the slide on the left, we can see a color point cloud produced by the LiDAR vendor's processing software using direct georeferencing. On the right, we can see our corrected point cloud. As you can see, we could fix the colorization issue caused by the incorrect image extrinsics, and we were able to provide more consistent coloring. Here is another example where we could fix the original coloring of the point clouds from the vendor's processing software. One of the challenges of recolorizing the points is that in our processing framework, the LiDAR and image data are decoupled, meaning that we don't have information which LiDAR points are from which images or views. Matching LiDAR points to images based on timestamps seem to be unreliable, since the two systems might not be time-synced properly. Furthermore, we wanted to allow our users to collect LiDAR and image data separately, so we could not rely on timestamps. Instead, we developed an algorithm that was able to recreate this missing relationship between the points and images, using only the geometry, and so it is able to assign images or views to the LiDAR points. The algorithm is based on the method known as Z-buffering in computer graphics. This algorithm can take into consideration occlusions during the view assignment process. Finally, the final color of points is computed from not only one, but based on all images that can see the points. That allows for a more consistent colorization of the overall point cloud. By combining LiDAR and photos and assigning views to each LiDAR points, we can create 3D textured mesh from the LiDAR points that are typically more reliable than points from the dense reconstruction. However, it is possible to create mesh from only a set of 3D points, but the quality of mesh can be significantly improved if we know which direction of the points can be visible. The view assignment process I just described previously does exactly that. Finally, the combination of the two sensors also allows us to derive orthophotos using the LiDAR points. As a summary, let's see what are the advantages of our workflow. Many drone LiDAR users are unhappy with existing software workflows and results and struggle to combine LiDAR with images. We are offering a solution for them. Our method allows for registration of LiDAR and photos to GCP controls or photos to LiDAR, where LiDAR is the control, or vice versa. The method is flexible, meaning that we can combine drone LiDAR scans with images, or aerial LiDAR scans with aerial images, or ground LiDAR scans with phone images and drone images. On my last slide, you can see my co-authors, Shichi Li, Benjamin van der Jagt, and Emily Blagwan. Thank you for your attention, and we'll be more than happy to answer any questions you may have.